it's a very complex thing. As I understand it, even people that study it their entire lives are kind of confused. But Stefan, you, sir, are actually a physicist, and I'm assuming that you'll be able to take all the hard questions.
I mean, it's a deep rabbit hole, man. I'm a little bit rusty with my quantum computing lingo, but I think I can at least engage in a reasonable conversation that the audience can enjoy. I think the peak of my quantum computing career is I built a simulator of a photonic quantum computer at an IBM hackathon about 5 years ago. But I have some understanding of this stuff, and it's a really, really cool space.
So, before our guest gets up here, why don't you give us just a deep dive? Tell us about the history of quantum mechanics, what it is, Heisenberg's uncertainty principle, all the things that people will need to know just to get up to speed before we get into quantum computing.
Wow, you could have briefed me on that before you pulled me on stage, mate. A brief introduction to quantum mechanics. Well, I think that it gets interesting when you think about the limitations of classical computing, which is everything is represented as a very exact piece of data in a transistor, so zeros and ones effectively. And of course, this is a very, very effective way of performing computation, but there are certain problems that require massive, massive phase space exploration or massive, massive memory requirements. And quantum computers are really, really good at sort of residing in a limbo of juggling lots of potential candidate answers and then sampling from basically things that are not just ones and zeros, but something that can sort of be balanced between the two of those. It's like a stochastic computer because nature is stochastic. Quantum mechanics is inherently about sampling from probability distributions, and quantum mechanics are a way of tapping into that extreme efficiency in certain problem domains. But I think a real expert has now stood on stage, so I'm going to quietly recede from from my lecture, and I'm going to let him continue the introduction to quantum mechanics and quantum computing. Beyond NISC, hey.
Hey man, how's it going? I thought you were on a roll.
Yeah, I often sound like I am, but it's rarely true.
So I'm a bit nervous that Const is going to ask me to explain a crazy quantum mechanic principle on the fly, man. That was a crazy drop on Crux. Also, by the way, guys, we should have Bongo Cat Feynman joining us also. So if he raises his hand.
Yeah, he's coming up now.
Yep.
All right.
Hello, everyone. How's it going?
Welcome, Mr. Bongo Cat Feynman.
Thanks.
Yeah. So I'll be really interested as we're going here how long it takes before somebody calls out my name in chat. You're more than welcome to say it if you know it. I will dox in slide number 2. Oh man, JB Ring, you got it already. Holy smokes. Record time. Well done, guys. Yeah.
I see Richard Feynman on there.
Yeah, right.
Oh man, I wish. Anyway, thanks for having us, guys.
Very cool.
So I'd be happy to just keep it like informal and chat for a little bit. I'd also be super happy to jump into kind of prepared material. I was actually going to jump into not the technicalities of what quantum computers are, but I was actually going to start off going pretty deep into kind of why quantum computing is really pretty critical right now and why there's a market for it. And I'd be totally happy to dive into that, or I'd be happy to spend just a little bit of time hanging out before we start.
Well, I don't want to ask you any questions that you guys are going to go and ahead and answer anyways in your slides. So why don't me and Crux will leave our questions. Hopefully they'll be slightly more informed by the end. And we won't sound so doofus-like. And we'll just go straight in. So like I'm sure in your slides you're going to present yourself and stuff like that. If not, we'll definitely ask you at the end.
Yeah, okay, sounds awesome. Let's just jump in and do it then. Yeah, so we will keep this pretty casual. We do have prepared material. Like I could tell stories all day long, every day. But do feel free to just kind of steer wherever you want to go as we're going, and we'll take you and your audience to that destination. So again, my name is Bob. I'm here representing Bittensor Labs, and we're really excited to be here today. We're going to take you through kind of a journey where we talk about why quantum first and kind of why quantum now. I also want to talk about why Bittensor, which may feel obvious to all of you guys, but to be honest, it was a little bit of a surprise for me, and it was like an exciting surprise on the upside. So we'll talk about that. We'll talk about the progress that we've made so far, and we'll talk about the vision of sort of where we're headed next. And then I'll be really excited to share some of the kind of big evolutionary thinking that we've learned from what we've already done in the last section as we go. And like I say, I can be a storyteller and just talk for a long time. So I'm going to force a break between each of these sections, but like really do feel free to just jump in and drop your questions on me. So yeah, about me, I'm Bob Wold. Nice job calling it out, guys. I've been blown away with how good you guys are at information discovery. A little bit about me. I've spent 25 years in industry. I'm the founder of a traditional quantum startup called Quantum Rings, which is, very much like a, I don't like I almost want to say like, real world traditional startup, although like the real world is way less exciting than, the world that we all live in here, to be honest. I've always been a deep tech enthusiast. I've also been like a massive skeptic, and I was a huge skeptic of crypto in general, which sort of, I will say, started me off kind of assuming that this journey was going to be sort of a quick little dip your toe into, the exciting world of crypto. But man, I decided I want to dive in head first. This is great. We're based in Boulder, Colorado, and some people have asked about the logo. That's totally the Boulder Flatirons. So if you guys like Google Boulder Flatirons, it's like a distinctive mountain range right by Boulder. And I go by Beyond NISC. All right, so enough about me. Oh yeah, the one thing about me, I've got, I am bullish on this market now. So why quantum? Well, quantum holds the promise to transform the world. That's like a super hypey thing. We'll have to dive into figuring out what that actually means. But Crux was actually onto it at the beginning, which is basically that like traditional computers are limited by how much information you can encode into them, like how far you can search within a search space. Quantum computers have this crazy thing where you can like encode the constraints physically into a computer, and it can represent all possible states in a space simultaneously. And so what that basically does is it can be applied to a specific set of problems that are like super big problems, super valuable problems that hold the promise to transform the world. And so like when I tell people about this in my day job, I focus on the fact that my grandchildren hopefully will live in a world where we've discovered cures to the most harsh illnesses. We can potentially cure AIDS, potentially cure cancer, because real-time computational simulation of new drugs will be enabled, where you don't think necessarily about how far you can get on your EV charge, because we've discovered better batteries that can charge faster, hold more energy, that have a lower impact on the earth to mine them, where we're no longer faced with like just the goods that are produced not being with the people that need them, because we can optimize supply chains, where today we have to approximate those optimizations because of computational limitations, or worlds where everybody's 401k looks a lot bigger because portfolios are being optimized. And it's not just sort of a directional promise. McKinsey did a study where they actually looked at each of these problems and experts in each of these fields and mapped the specific problems with the market that they were going to create and with the functionality of quantum computing and quantum algorithms. And they estimated that the first market's a $400 billion market. In the materials space, you have a $500 billion market, $600 billion in logistics, and $600 billion in finance. Now, I sort of misquoted that. It's not a market, that's the economic value creation by solving these problems, meaning that, we're unlocking by 2035, potentially $2 trillion in economic value if quantum computers can hold their trajectory, which is pretty damn exciting. And so, like, I'm hoping, Const, you're feeling good right now? Are you feeling bullish?
I am. But how does it all connect to Bittensor, though? This is the big question.
Yeah. All right. Let's get there. But well, before we do though, I just gave you like the peachy story, so let me also tell you the real side of it too, and then let's connect in Bittensor. So, like you're like, okay, well, if you can do all this awesome stuff, you're going to totally revolutionize the world. Then like, why didn't you just cure cancer already? Right? Like, let's do it. Let's go. Well, it turns out that quantum computers are really, really hard because they require you to isolate physics and stop them from physicking with the rest of the world, right? And so that's why you see these things in like these giant super refrigerators that, you know, get down to 0 Kelvin, right? Physics are very hard. And so in the real world, there are very few of these computers, so you got to wait in line. They're super noisy and error prone, and they cost gobs and gobs of money. And so like to put some numbers on those, I have to wait hours or days for quantum computer. Like yesterday, I had to wait 12 hours to run on IBM's quantum computer, and that's not abnormal. It's not like that was a long wait time. They have huge error rates between 0.1% to 1% per operation. So that's not per program. That's like essentially per line of code in the quantum world. And they cost, you know, if you think GPUs are expensive at like $2 to $4 an hour, try spending, you know, $5,000 to $15,000 per hour on them. And so if you're the people saying like, oh man, I'm going to go solve these billion-dollar problems and transform the worlds, you are blocked, right? You're sort of stuck by this. So maybe you're not feeling quite as bullish anymore. No, it's still good. It's still good. So the people that know kind of know that there's two sides to this story. And so if you look at like Jensen, CEO of NVIDIA, he'll talk about how exciting it is because they're going to solve these exponential problems like simulating atoms and molecules for drug discovery. You're just going to need several million physical qubits. Or you can look at Sundar from Google, and he'll say, you know, yeah, we're going to totally learn the basic structure of molecules that we're sort of missing today, except you're going to need a totally fault-tolerant quantum computer to do it. Still a bull. Or Satya from Microsoft, who talks about, you know, lossless power grids, carbon capture from atmosphere, quantum computers so powerful we can model nature itself. Totally a bull. And so like all of these guys are equal parts like excited and not excited about it. Or they're excited, but they're realists about it. But the cool thing is that, and this is sort of tying into why Bittensor, you know, you guys probably are super familiar with AlexNet. I probably don't need to explain that to this audience, but just in case, in 2012, AlexNet was released and it kind of blew people away with how accurate that model was. And then once they put that model out there and everybody else started working on this problem and really democratizing it, thousands of smart people trying to do better, you can see that in the 7 years that followed, you could get AlexNet performance with 44 times less compute. And that's freaking awesome because lots of smart people working on these problems get you to innovation. Well, history is kind of like starting to repeat itself in that if you take a look at some of the really exciting quantum things, like, okay, in this case, those RSA ones are around breaking encryption. FOMOCO is about, you know, simulating like a very important molecule. You know, there are these different quantum algorithms. You can see that how big a quantum computer is going to have to be to solve these algorithms is getting better because the scientific community that's working on them is making the algos more efficient. You can also see that quantum computers are getting better, like the qubits themselves are getting better. This particular chart happens to be from Google's, Google's Willow processor. This is about coherence times of qubits, which, you know, one of the users on Twitter had asked us about coherence times. They're getting better, error rates are getting better, error correction's getting better. All the charts are in the right direction. And so when I think about that, I was reminded of this DARPA slide from the DARPA QBI conference that I was at in DC in February, where they put up this chart of like all the different quantum problems scatter plotted across the size of quantum computers on the bottom and the number of quantum operations. And so you can sort of see that like some problems are going to require huge numbers of qubits. Some are going to require just a few qubits. But the cool thing is that the quantum computers are getting better and we have these problems getting easier. And so the conditions are sort of like just right for this thing to go to the moon. Okay, this isn't like like to the moon. Maybe it's about, you know, make no financial projections, but I mean like quantum is ready to go to the moon, right? The problem is going to be that scarcity is going to remain. And I literally was talking to the number 2 quantum computing company in terms of logical qubits. And I asked them, how much is it going to cost to buy one of these quantum computers? He says, I can sell them for N million dollars. And I'm like, that's awesome. How much is it going to cost when you have 100 logical qubits? And he said, I'm not going to sell them when I have 100 logical qubits, because once I have 100 logical qubits, I'm going to solve the world's, like these handful billion-dollar problems. The only way people are getting access to them is we're co-developing IP. And so power and scarcity make people do strange things, right? And I think that's like what the quantum world is like, even when it's bad for everybody in the end. And so that is why Bittensor couldn't come at a better time. So when I first saw it, I was first impressed with your graphic, but I was quickly way more impressed with what came after that. So I was actually reading this. I printed out like all of Bittensor's documentation because I was trying to wrap my head around how everything worked. And I came to this part and I had to grab a pen and start highlighting things because I saw this line. Bittensor simply defines the market, which will reward. Like, okay, so we're going to have a market, we're going to reward. We're not going to define how you solve the problem. We're going to leave space for innovation around how that problem will be solved. And then we're going to open it up to thousands of incredibly talented individuals across the earth who achieve that aim in various and creative ways. Right? So it's starting to kind of click, right? I think people are maybe like, I don't know, I get goosebumps when I think about it. And the crazy thing about that is, I think I shared a link on Twitter recently, which was a video from Pete Shadbolt, who's the chief science officer of PsiQuantum. They're like one of the best funded quantum computing companies in the world. And I'm just going to play that video for you real quick, or just a section.
If I think about the history of the semiconductor industry, self-driving cars, rockets, robotics, and so many other technologies, to me, it really doesn't look like a story about breakthroughs. It's a story about grind and about sustained and dogged progress over decades. It's about leveraging capabilities from adjacent fields, about desperately trying to keep things simple. And most of all, it's about taking something that everybody said was impossible, something that's been impossible for decades, something that's failed and failed and failed, and dragging it, kicking and screaming, over the threshold of usefulness.
Right. And so I'm not the only person in quantum thinking about it this way. So I'm going to say, Pete, I'm going to go ahead and just, say that he's a bull too. And so, I mean, we talked about like, those algorithms getting better, but the only people that can innovate in quantum today are quantum people. Like, it's a very exclusive club. We opened it up with 63 and we invited Bittensor people to innovate, and they're already innovating in an incredibly impressive way. But we want to go a lot further. And so, like, I think most of you have seen the roadmap, and we'll get to it really soon, which is that we want all smart people having the ability to innovate in quantum. Or even if you're dumb, we want anyone innovating in quantum, Screw it. And so, like, when we started with Bittensor, and I told you I was a skeptic, like, so we came in here and I was like, yeah, okay, grift. We're going to find, that's just going to be grift, like, watch your wallet. But actually we found, like, okay, there is a little bit, there's these little pockets of grift, but for the most part, we saw grit, and we were sort of worried that, maybe it's going to be like a bunch of, mouth breathers. That is not the case at all. Like, we were blown away immediately by the intelligence that is created. It's not like and I don't even know if it's like it attracts intelligence or if it like fosters intelligence and grows it. And, we thought it would be people looking for easy money. And there is like a fair share of people looking for easy money. But like what we saw a lot more of was that the money goes to those who do hard work. And so, yeah, we've just been really excited with what we've seen here so far. Okay, so I told you I can be like a storyteller and just talk forever. So I better like breathe for a second. I'm going to take a drink of my coffee and pause, and then I'll totally keep going.
I don't want to interrupt you. I think everyone's loving it.
All right, sounds good. Well, we'll keep rolling then. Yeah, so far, we launched the quantum subnet. And the quantum subnet on Subnet 63 focuses on giving users hard problems that have to be executed in a quantum environment. We're doing this because we want to get Bittensor educated on what a quantum circuit is, what quantum simulations are, how you can optimize a simulation, how you can understand the quantum mechanics that are working encoded into the circuit to optimize the circuits to find even more innovative ways to go. And I'm going to have Will, or Bongo Cat Feynman, take us through a couple of what those circuits are. So, Will.
Yeah, hi everyone. So my name is Will. For the past several years, my background has been in PhD research, academic research in atomic physics and quantum information science. And I'll say I'm a very new person to this whole qubit Bittensor thing. But you know, in the short time that we've been here already, I've been super impressed by all the innovation and ingenuity that we've seen from our miners, and I'm really excited to see, you know, where we go from here. So I think at this point it'd be good to dig into some technical details about what's already going on in Subnet 63, and we can you know, take questions from anyone as they come. I think that'll be good. Okay, so we launched Subnet 63 with this idea of a peak circuit, right? And these peak circuits are a particular idea that, you know, have been launched recently by Scott Aronson and his collaborator Yushen Zhang. And they're an attempt to solve this open academic question of how do you verify what a quantum computer is doing, right? So you can say you build like a quantum computer, you build some like neutral atom experiment or trapped ion experiment or something, and you shoot them with lasers, you do whatever you want with the system, but how do you verify that the result is kind of doing you know, what you want, right? This is an open research question, as I've said, and these peak circuits are kind of an ideal starting point for sort of a nice problem to have on the subnet for miners to solve for themselves to start, you know, get them started understanding quantum. Because yeah, I'll get into the reasons why in a sec. So okay. Oh, that's weird. Okay, the slide control is weird. Okay, anyway, so what are peak circuits, right? So the fundamental thing to understand about quantum computers is that what they're doing is not actually so fundamentally different from just mere probabilistic computing. There's like some funny sort of complex numbers going on and wave interference and so on, but fundamentally what we're still dealing with probability distributions. And so the concept of a peak circuit is, I'm going to leave it as a black box for now, right in the middle. And it's this kind of set of operations that you can do to take some initial sort of flat uniform probability distribution and introduce a peak on some particular computational state. So there's like a particular set of bit strings that are explorable in the system, and you pick one of these bit strings and you introduce some slight peaking in the probability distribution. And so the task that peak circuits sort of perform, right, is this peaking. And as a challenge to put out to the miners on Subnet 63, the task is to find the particular computational basis state on which there is peaking, and that's sort of the concept of a hidden bit string. So as I've said, this idea was originally put out by Scott Aronson and Yushen Zhang. There's the archive link for anyone who wants to take a look. I highly recommend this. There's some great insights, and it's actually a very approachable paper for people who aren't necessarily so familiar with quantum computing. But nevertheless, this problem is it seems to be a very reliable thing for the whole problem of verifiable quantum computing. And additionally, I'll say that it's a very approachable idea to people who are new to quantum computing in general, right? The idea of finding this hidden bit string in the set of all others from this probability distribution is something that I think a lot of people can wrap their heads around. And it's, as we'll see in a couple of slides here, well, it is the task for, well, it is you know, kind of a usual thing that you might want to use a quantum computer for. It's not necessarily representative of kind of the rest of the, you know, quote unquote real problems that you might actually see in quantum computing. But nevertheless, peak circuits are also an amazing starting point because they're actually very hard to compute. because physically, from a physical standpoint, the fundamental thing that differentiates quantum computing from classical computing is the existence of quantum entanglement. And specifically, this is exactly the thing that makes it hard to sort of simulate on a classical computer as well. When you have a lot of entanglement in the system, there's lots of extra information in the probability distribution that you will have to keep track of. It's typically thought of as sort of a distinct kind of entropy, in addition to sort of the classical Shannon entropy that some of you may have heard of. And this introduces a fundamental exponential bound on what's going on in the quantum computer that classical computers have to contend with. And the real thing about peak circuits is that, wait, let's see, there's supposed to be a graphic on this slide. Anyway, Bob, do you know what's going on?
Nah, man, your beautiful chart is not there. Hold on. You want me? I mean, I can try to see if I can get it to come back. You want me to try?
We can imagine it, right? It's the complexity of the circuit, and then the randomness or the entropy increasing in the complexity of the circuit, or the amount of entanglement.
Yeah, well, it was kind of supposed to be the layout of what these peak circuits look like, but I mean, it's not so important for what I'll say, I guess.
No worries. It was a sick graphic. I'm bummed, but that's cool. We'll screen grab it and throw it in the chat afterwards. I'll go see if somebody pulled it out of the Google Slides.
All right. Oh well. Okay. So anyway, so the idea behind peak circuits is that they are basically one step short of a completely random circuit. So you can think of just a random set of operations that you're doing to this quantum state. And there are lots of properties that people have proven about these random circuits, but one of them, just naively, is that they create lots of entanglement. And so this is where the real appeal of putting this out to the people on Bittensor comes from. So we know that they're used to throwing lots of compute at these problems. They're very good at managing all this raw power. And as far as we've seen on Subnet 63, they've done a great job of applying it to this problem of simulating peak circuits. But as I've kind of talked about a little bit before, one of the most fundamental things about being able to actually innovate in this space, in the quantum computing space, is that there are lots of trade-offs that you have to make. Right? The fundamental idea that basically all the research is pushing into is that you can very easily scale up your systems to sizes where this exponential cost kind of takes over and you hit basically a wall. Right? We're right at the frontier of kind of what's really doable on classical computers. And so what it really means to innovate in this space is to sort of, I'll co-opt what Pete was saying in the video that Bob showed earlier, right? Is that you have to really claw your way into sort of the space beyond the boundary, right? You have to drag your, in this case, the classical computers, kicking and screaming into the realm of the quantum as far as you can. And so one of the very prominent ideas in how to in the research that's relevant to this area is making trade-offs between accuracy and speed. So you can do a very poor simulation of a quantum computer, right? For that could run very fast, but you won't be able to have high fidelity, of course, in whatever answers you get out of your simulation. Or you can spend a lot of time getting your accuracy right, but then your computation is going to take like 10 billion years. But I want to add sort of one third idea to this trade-off, and I'm going to say the whole idea of applying brute force compute to these problems is actually another contention, because what really needs to happen, I believe, and many other people that I work with believe, is that in order to really innovate, still, you need to also apply your brute force compute properly, right? That is, you need to all of this is open research questions. It's filled with hundreds of people and thousands of people in academia doing the same thing with coming from a different perspective. And so the real question is, can you also make algorithmic improvements? And this is something that I'm really excited for, because we're opening up these quantum problems to to a wide range of people who are very good at managing raw power, and we're asking them to figure out what the best avenues are for applying that raw power. We're asking them, can you come up with new algorithms to be able to run these quantum problems and solve them in entirely new ways that no one has thought of? And so this is kind of a fundamental thing that I wanted to illustrate, a fundamental point that I wanted to illustrate in sort of the design of the second problem that we introduced to Subnet 63, which we're calling hidden stabilizers. Now, hidden stabilizers are not sort of an established idea in the way that peak circuits are, but really we were designing this problem in order to really drive home this point of the fact that you can't just throw a bunch of computing at these problems. You need to engage with the underlying concepts. So we can go, I guess maybe this is a good point to take any questions from people if they have them on peak circuits. Otherwise, we can dive into this second problem.
So can you explain a little bit more what you meant by the difference between accuracy, speed, and brute force? Like, what is this other dimension?
Sure. Right. So there exists, many different ways to simulate a quantum state in a quantum computer, right? And one of the leading, I find that this concept is most easily crystallized in that of the sort of matrix product state. Is that a familiar term?
The matrix product state?
Yeah.
Stefan?
You're summoning me into this. I have a different line of inquiry, but don't just entangle me into your own.
I actually am not sure about what the matrix product state is. I was hoping Stefan, my co-host, would save me.
Okay, yeah, totally no worries if it's not very familiar, right? I'm sure that people are familiar with tensor networks, though. Am I right?
I think a fair amount of the audience are quite AI familiar, but you might want to introduce it a little.
Sure. Okay. So tensor networks, right, are kind of a way of spreading out a sort of linear algebra-based computation among different parts, right? It's taking like a bunch of matrix math. In principle, it's like it's like multiplying a bunch of matrices together, but it's sort of decomposing it into many small pieces that are easier to manage, right? And one thing that I'm personally not an AI guy. I'm only a quantum guy, but from what I understand, a lot of these concepts are drawn from AI. So I'll speak from that viewpoint. So when you're working with tensor networks, right? There's this fundamental trade-off between accuracy and speed, where when you're sort of breaking your large computation into different parts, you can choose the precision with which you're doing the kind of decomposition. Right? You can choose to throw away a lot of information in exchange for speed, or you can keep that information and have your matrices be a lot bigger, so that when you have to then go and do all the matrix multiplication, it just well, right?
Yeah. So it's accuracy, speed, and effectively cost.
Yes, that too. Cost is another factor. I guess usually people in academia don't think quite as much about the cost of these large.
Point.
Okay, but anyway,
I understand.
Yeah. Okay. So tensor networks. So matrix product states are kind of a translation of these tensor networks to the problem of simulating a quantum state. And it's a way to break your large quantum state vector. People traditionally think about it as sort of an array of like 2 to the number of qubits, number of complex numbers. But a matrix product state is sort of an answer to the question of how do I break this quantum state with some tunable fidelity into small little pieces in the same way that you would do for a large tensor network computation.
It's a matrix decomposition that allows you to parallelize the compute.
That's right.
I think if I can dive in after that. So I certainly understand that within Bittensor, we speak the language of what we call synthetics and organics. Synthetics are the things that keeps the machine warm and make sure the miners are doing something useful. Organics are kind of where the rubber hits the road, where real users inject their queries and the miners are hopefully, very well optimized to serve those queries with high quality responses. So these, the peak quantum circuits are a really natural choice for, you guys have that sort of nice asymmetry where the validator can quickly verify, okay, the qubit strings match the probability distribution is strongly peaked around the expected area. Therefore, you guys can, reduce the amount of work the validator does. That also means that everyone in your subnet doesn't have to suffer from validators wasting their time and energy trying to recompute these really complex problems. But I guess the question from me is, do the peaked quantum circuits provide intrinsic utility? Like, are there organic queries that would map onto peaked quantum circuits? Does this actually, do you know what I mean? Does this track the production distribution of real use cases, or is this just a very useful heuristic to make sure that miners are doing things that aren't just sort of naive classical algorithms?
Mm-hmm. Yeah, well, I'll say two things. First is that you were saying earlier that these have in principle nice value for validators, and that there's just like a single bit string that they check. I'll say that it is true, but in this case, one interesting thing that we've seen in terms of the operation of the subnet that we've been hearing about is that these peak circuits are actually quite hard to generate, and so I'll call out this specific feature of a lot of quantum problems that have been a major obstacle in the theory for us to get over, is that a lot of these quantum problems are very symmetric in terms of like how long it takes to create like a problem, like a circuit, right? And versus how long it takes to solve them. But then this is one of the things that we've done some innovation on ourselves in terms of optimizing all of these computations that have to be done to feed the beast, basically feed the beast that is there's all these voracious miners who are hungry to throw the compute at something. But then to your second, I'll talk about sort of the value of these peak circuits. Most of these peak circuits are not directly representative of kind of real quantum computing problems. And what our major aim was when we launched 63 was to start introducing these quantum concepts to maybe a crowd of miners who were maybe not so familiar. And so this illustrates some of the fundamental points. It's not directly a problem that people would solve, but it is a valuable research idea in terms of maybe like running some test benchmarks for a quantum computer when it's sort of initially constructed and making sure that it's doing the right thing before you then get on to the real worthwhile problems as we are planning to do in the next in the near future on 63.
Yeah, and maybe I'll jump in just a tiny bit.
Please. Yeah.
Yeah, no worries. And then hand it right back to you here, Crux, to pick up where you left off. But, the original value that Aronson and Yushan had in designing this was essentially to come up with an algorithm that you could use to actually prove that there was a working quantum computer. Like, how will you know when a quantum computer, like if you're giving them problems that are so hard that they can't be solved by regular computers, how will you know they got the right answer? And so you sort of need these problems that can be of lots of different sizes and complexities that somebody validating a quantum computer knows, but then it's so complex that only a real quantum computer can get the answer. And so verifiability was sort of the original use case. Now, how that maps into Bittensor is kind of really exciting because essentially, like in that model, the validators are literally the validators. Who can generate these circuits and understand what the final answer is supposed to be. But you can make these things like exponentially complex so that, we can push the limits of what people can do. And so by incentivizing miners to go bigger and bigger, you're essentially encouraging them first to take existing simulation technologies and figure out how to scale those, like across large HPC, which is a really useful problem for the world who's trying to develop algorithms. But then second, it's to say, well, now they've designed these circuits to try to be like something only a quantum computer can do. Well, can you innovate in a way that allows you to scale larger than you would expect mathematically to be able to scale running on classical computers? And so when we do get into kind of like the roadmap and next steps, we'll sort of talk about why this first stage of like really pressure testing the community and seeing how they can scale it sort of translates into, I think, your earlier question, which was sort of around like you use some cool terms for like, one type of problem to kind of like get the community going, and then another type of problem that actually takes like almost like a two-sided market of problems and actually start solving them. And that's exactly the direction we're headed.
I believe I owe actually Mog Machine credits. He's the first person I recall using the term synthetic and organics. Back, a year and a half ago, everyone was just talking about synthetics. Like, how do you, procedurally generate problems on the fly that miners have to solve? And then obviously there was a point where subnets had to actually serve real user queries, and that's where organics came in. So I'll take no credit for the language there. I'll give Mog Machine a credit. But you guys are giving me a million jumping off points here. I'm aware that you've got probably loads more great slides to get through, so maybe I'll just hold off and let you guys crack on.
Sounds good. Well, don't let us stop you, but we do have some exciting ground. I have a feeling that by the time we sort of start dropping some of the big things that are coming next, these questions will sort of like, interest may have moved to the big things coming next. So please don't hesitate if you have things that you want to make sure we hit to hit them before we move on. All right. So Will, maybe I'll hand it back and you can keep rolling into HStab.
Sure. Yeah. Sounds good.
And maybe one of the things that, maybe we should contextually say is sort of why we introduced HStab so quickly.
Right. Exactly. Yeah. So I guess I'll return to this trifecta of accuracy versus speed versus brute force compute, because as I was mentioning earlier, right, a huge part of what innovation looks like is coming up with new algorithms and really interacting and engaging with sort of the quantum information that's going on behind the scenes. And so this was our attempt to really illustrate the point of this third dimension to this trade-off here. Because what we're going to be talking about is sort of what's known as the stabilizer formalism. And so this the stabilizer formalism it really underpins a lot of the current research of quantum error correction. This is a very hot area of research because it's basically the thing that will allow quantum computers to scale much larger than they are currently. One of the things about quantum computers is that they're very prone to sources of error and noise, but error correction comes in and solves this problem in the same way that classical error correction does, but it's much more complicated because there's different sort of quadratures of degrees of freedom that are involved with the physical qubits and so on, and we don't have to get too far into that. What I want to talk about in terms of the stabilizer formalism as it applies to 63 is that it's all very mathematical, right? There's a lot of nice theory and math that goes on behind the scenes, and what we really want to do going forward and leading into the rest of our roadmap is to introduce these concepts and make sure that our miners are at least familiar and preferably quite comfortable with all these concepts so they can make major improvements as we go on. So when I talk about stabilizers, when people talk about stabilizers, they often talk in terms of these special sort of single qubit matrices, these X, Y, and Z. Right, so these are 2x2 complex matrices, and a lot of what goes on here is building lots of mathematical structure on top of these small little moving parts. So what we're talking about here are these three matrices in addition to the 2x2 identity, and we talk about sort of the set of all these are called Pauli matrices. They show up all over physics and even a lot of kind of pure math, right? So these are Pauli matrices, and we can talk about the set of all sort of n-ary tensor products of them. So I have this curly p sub n. We can talk about the length of we call them Pauli strings, So these are tensor products of Pauli matrices up to an overall sign that's plus or minus. And we're going to talk about n-ary Pauli strings that correspond to operators on the space of n qubits. So you can imagine a register of n qubits in a quantum computer, and then these are special operators that we can apply to them. They have a particular property that for a certain kind of subset of all possible quantum states, the state can actually be entirely specified by a set of, some number of these n-length Pauli strings. And we call those stabilizers. So each stabilizer is a Pauli string of length n, and we can use some number of these Pauli strings as the stabilizer set, which I'll call the stabilizer set that completely specifies this quantum state. And so this is one of my favorite pieces of quantum information, actually, because it's an entirely different approach to specifying how you can represent a quantum state in a computer's memory. As I've said before, people are usually used to thinking of state vectors as these 2 to the n length complex valued arrays of numbers. But instead, you can treat them as just bits in an array, as I'll show on the next slide. Whoops. Okay. But one really key property that the subset of stabilizer states have is that you can actually get a computational advantage through reasoning about these small little parts and this alternate way of specifying a quantum state. And it takes the form of sort of a Clifford algebra. This is the mathematical formalization of how you can multiply all of these small little pieces together. And what I'm showing over on the left here is sort of the key multiplication table that characterizes what this Clifford algebra sort of behaves like on an abstract level. And through this Clifford algebraic reasoning, what you can do is realize what's known as the Gotsman-Nil theorem, which is that which can be summarized as saying that stabilizer circuits and stabilizer states can actually be simulated in polynomial time. And then so this is very strongly counter to the notion that all quantum computing is fundamentally exponential. And sort of the crystallization of this is what's known as a tableau. This is a binary matrix of some number of columns and some number of rows, where all of the entries x and z and r are ones and zeros. And if you use this representation of a quantum state, then what you can do is actually simulate a circuit in polynomial time. And so this is sort of a paradigmatic example of how clever reasoning can lead you into some very real advantages when it comes to making headway in simulating larger systems of qubits. And so anyway, so as it pertains to the hidden stabilizer problems that we have on 63, I'll just go ahead and state the challenge just for thoroughness, right? So given a quantum circuit that operates in this regime, in this restricted regime of stabilizer states, the question is the challenge is to simulate the whole circuit and then find the stabilizers of the output state. So this is a fundamentally exponential task because there are 4 to the n. There are 4 to the n possible Pauli strings that can apply to an n qubit state, and you have to search through the space for a set of these special Pauli strings that satisfy some given constraints and some additional constraints with each other. And so this is a sort of a fundamentally hard task that is quite immune to brute force, I would say. And already as I'm speaking, this is not even 3 weeks, I think, since we introduced the challenge, but our miners have already demonstrated their extreme ingenuity and broken through the problem and realized how to interact with the underlying quantum information and break the problem through cleverness. And so this is something that I've been really excited about, actually, because it demonstrates what our miners are capable of, Bittensor is capable of, and it makes me really excited for the plans, I'll say, that we have for the future.
Totally. Yeah. And so maybe just to sort of restate that at like the, 10,000 foot level, you have this problem that's actually a super complex problem. But by carefully understanding how the problem is formulated and understanding also like outside research that's been done, you can sort of connect the two and turn this problem into something that actually is fairly straightforward to simulate to get the same answer. You can essentially pre-process the circuit and make it something that's fairly easy to simulate, even though the initial problem is, incredibly hard to simulate, which is quite innovative. And so maybe oh yeah, please.
I'm hoping that we're going to get to see some like statistics, or should I ask about that now? Because I would love to know, like, yeah, how well are we doing? How do we measure that?
Yeah, so in this particular case, because of the way that okay, so I think the way that this innovation was done, essentially it's become unbounded. So essentially it transforms all of these gate operations into gate operations that are very easily simulatable. And you could potentially go up to thousands of qubits with it. Now, that's not a universal pre-processing solution. It's, essentially because of the nature of the circuit. But what it demonstrates is that instead of people just figuring out how to scale a simulator, which is what they're trying to do with the peaked circuits, they also took it from a different angle, which was to say, can I actually understand what the circuit's doing, analyze the circuit, and then write a step that sort of does the same thing in an easier to execute way. And so once that was discovered, it essentially became unbounded to the point where, peaked circuit, not peaked circuits, H-stab circuits have now been disincentivized and will be retired. Essentially it goes in the Hall of Fame because the community was innovative, which is great.
Wait, so before you took this problem to Bittensor, had this solution been discovered in the industry?
Will, I would say pieces of it, right? I would say that this was the combination of pieces, but no, I don't think. I don't know that I've had somebody put all of the pieces together yet. Will, you would know this better than me.
Oh yeah. So like when we were sort of going through the steps and designing this problem, it's sort of a well-known fact that this restricted regime, has all these theoretical advantages. But as far as what we were doing, designing the problem, we sort of could make a good guess that there was some nice strategy to be found. But as far as we knew, there was no strategy that already existed. So this is an example of our miners coming up with something new that worked for them.
And like in the industry, is this something that is benchmarked, like, or is this something that can be written about in terms of a paper and say like, hey, this is quite novel. Look, they did this. This hasn't been done before, and this is valuable not just to you guys in your subnet, but also across the field.
Yeah, certainly there's a potential. Of course, we don't know exactly what our miners are doing. We only know that they've solved it very quickly. What we have currently actually is sort of the reservation of a nice pot bonus for anyone who comes forward and kind of releases their solution by the time that we retire the circuit. So potentially, when we can get in touch with whoever comes forward and claims the pot, we can work together with them and try to publish their results.
Have you guys looked at actually moving from what I'll call black box, so the miners optimize sort of behind their APIs, to something that forces them to submit these algorithmic innovations and share them in order to be rewarded? White box.
We would love that. So that was, honestly, when we launched, one of my biggest concerns is that people wouldn't share because they would be essentially incentivized to hold on to the secret for as long as possible. So, I would love to pick your brain, Crux, on like ways to do that. Right now, the best way we could come up with was following a pattern that we've sort of discovered, which was to create an incentive pool where we basically hold, some of our alpha back and then offer it as a bounty to publish. But if you have other ways of accomplishing that, I'd love to chat about it.
Well, I won't claim to be the expert on it. I know there's other subnets that are they're deploying that to great effect in other domains. I think a bounty is an interesting way of doing it, but if you put it front and center of what the miners have to do is they have to innovate, and then they have to share it. They have to publish it in some way that you guys can get your hands on in order to be even considered. There's a path that exists there. I would say that's already been quite well established in Bittensor, and I think that it would be super powerful for you guys to be able to publish what you're finding the miners are coming up with. And it sounds like it would be really useful to the research community and in industry.
Yeah, and I see some of the community here piping in that Ridges does this, 62 does it no, and I mean we're big fans of not reinventing the wheel. In fact, we'll talk about that a little bit when we talk about what's coming up next too, which is essentially drawing drawing inspiration from some of the other great subnets that we've seen and sort of applying some of those to sort of forward-looking quantum use cases. But yeah, we'll definitely take a look at Ridges to look at how they incentivize the opening of this, because I mean the democratization and the progress within quantum, really is a huge part of why we originally came. And so I saw just another funny thing. I had the pleasure, because Will's been covering the presentation so much, of seeing a fun question from Mark Jeffries too, that said, how soon can I use Subnet 63 to break shores and steal everyone's Bitcoin? So yeah, you might have seen on that giant chart from DARPA. Actually, hold on, let's go back to it real quick. I'll show you kind of roughly where that is. And then we'll come back. Oh man, look at all those animations. All right. Man, it's a little hard to see because our designer pulled the color out of this, but that little guy right there is 2048-bit RSA. And so you'll be able to find papers of sort of like people are always advancing how to do shores in more efficient ways, taking less quantum operations, fewer qubits, and you can find papers on that, but it's pretty big. It's a pretty far ways off. And one of the cool things about it is that, again, if you sort of say quantum computers are getting better, algorithms are getting better, one of the best things to do is to sort of do that in the light so everybody can see it. And so as progress is being made on this, I think, the entire world is kind of carefully watching it. Now, I do think, oddly, the crypto world, who should probably be the most concerned about it, seems to be like the least loud about it, but yeah, eventually that time will come. And catching back up to where we are.
Yeah. Can you keep us ahead of the curve there?
We can. Yeah, we can. And yeah, we absolutely will. In fact, so I was going to sort of not put a name on this next slide here, but I'm going to put a name anyway, which is, okay, so we put out peak circuits. That's still going strong. Those are super hard. The community is making nice, slow, steady progress. They made short work of the H-stab circuits. And so obviously we have more circuits coming. We weren't going to say what the next one is. I've got it all blurred out here, but I have the original author's photo behind it. But I will say the circuit that is on deck for 63 is actually intended to be a Shores circuit. And so the miners essentially will be incentivized to try to go larger and larger in terms of what they can break there. Now, this won't actually be the way to break crypto or to break encryption, but this is a way to basically figure out how you can scale using Shores as the test bed for it. Now, this is still in this synthetic, as Crux had said, sort of stage of quantum, and we are still moving towards that organic stage of quantum. But this will make for, we're hoping, a nice, exciting challenge for miners to sink their teeth into as we continue the evolution of the roadmap. And so, this has been moving at a breakneck pace. We were introduced to Bittensor like in May, late May. And we were introduced by some folks that were in town and were happy to transfer a subnet to us for the right price. And so we bought one on June 18th. We launched we launched the white paper for peaked circuits on June 30th and put the subnet out on July 8th. By July 16th, you guys had already scaled up to 36 qubits, which we knew you could get to, but I was surprised how quick you got to it. By July 26th, made it up to 37 qubits. Now, it doesn't sound like a big thing, but especially using state vector methods of simulation, which, from all evidence we can find, people have to do for peak circuits so far, for the complexity of peak circuits we're producing. So 37 is actually requires 2x the computational resources as 36, so that's pretty big. We quickly launched HSTAB because you guys are making too fast of progress on peaked circuits, and they're very hard to generate. And again, by August 12th, you guys had solved that completely, which is an incredibly impressive feat. So today we're on novelty search, and we're excited to kind of announce the next big thing. So, if anybody thought that Shor's circuit was the next big thing, that's actually the next small thing. That's kind of the regular cadence of kind of maintenance on 63. And so before we announce the next big thing, we want to go back to vision, just recognizing that not everybody had the, had read up on this ahead of time. And so we set off with the vision to make quantum computing available to everybody. And if you say, let's work back from that, how do we get to quantum computing for everyone? We have to have free access to quantum, which means you have to have an open quantum marketplace, which means you need to have real quantum end users. You have to have miners who are running QPUs. That's like real quantum computers, right? Those incredibly expensive resources. You need miners running simulations too, because 90% of what's done today, that's probably a low ball estimate. More than 90% of all quantum execution happens in simulators today. So we need to be able to do that. But in order to get quantum end users, we need a quantum company, like a legitimate quantum company. And we need financials that work so that a quantum company can actually buy into this, feed data into the open quantum marketplace, and the open quantum marketplace can survive without running out of money. Okay, so it's starting to get complicated, but bear with me. In order for miners to be running simulations, they have to be comfortable with quantum, which is why we need them running on synthetics to get started. And most importantly, we need proof of compute for quantum, which doesn't exist yet, but we have a first version of it, and we're continuing to refine it. And we have to have the ability to do cost estimation so that as quantum circuits are coming in, we can actually understand in a very accurate way how expensive should this be, and therefore how big should the reward be to miners who simulate it. And so when we outlined our roadmap, our original roadmap was to create these, again, I love the term synthetics. The first is a very narrow set of synthetics that are provable. And this allowed for experimentation in the community, for them to get oriented with quantum, for them to come up to speed. The second was to get into synthesized problems, what we called. So this was very small, controlled versions of real problems. But in order to do this, we have to have proof of compute, and we have to have dynamic scoring. And then ultimately to get to an open quantum platform. Now, we've been so excited with how fast things are moving. And we've learned a lot about how the incentives work and how people try to work with the incentives, work around the incentives, how the different types of incentives attract different types of miners. And we sort of looked at this and we said, hey, this proof of compute thing, we really need to get that good. If we don't get that good, then people are going to be cheating. And this dynamic scoring, again, if somebody gets something and we had it rated as a very low score and it took infinite amount of compute, that sucks. So we need to get that right. And we also recognize that we were incentivizing innovators, and we've been really amassing a lot of innovators on 63. And ultimately, we're going to be incentivizing operators in phase 3. And so we said, okay, well, let's just take a fresh look at this. What if phase 3 actually became phase 2? And we started with real quantum computers first. Because despite how we believe that the future is decentralized, the truth is that real quantum computers are very few and far between. So we can actually ping those platforms to confirm that circuits were executed. That means that synthesized problems becomes phase 3, and we can continue to keep an innovation ecosystem alive, driving continuous innovation that feeds into this execution environment as new quantum backends. So it doesn't end. The innovation doesn't end. It doesn't switch to operation. We have innovation and operation. And over time, we bring on additional QPUs. And once proof of compute is bomb, we bring on simulation, and we let everybody bring their HPC to put jet fuel on the scientific community and really tear this thing open. And so it's with that evolved thinking that what's next is we purchased Subnet 48. And what we've been calling quantum on 63 is where we are going to innovate. We are going to continue to challenge quantum miners to figure out new ways of creating, new ways of simulating. And all of that innovation is going to feed into the quantum compute, where it will be operation, right? This is going to be where people are bringing the compute resources, and we're creating the two-sided market. Now, if that's all kind of exciting to you, I said we have to have a quantum company. And so, Bittensor Labs was really formed to be able to experiment with all of this in a very safe way where, I'm potentially, exposed to the crypto world, but my quantum company is not. But what we're actually going to announce here is that we've formed a partnership to launch Open Quantum, and we're targeting the fall of this year to open this. And Open Quantum will be a marketplace where we have quantum users on one side out there executing circuits, submitting them to validators who hand them off to miners, and the miners execute those circuits and return the jobs, going completely into the organics. And the cool thing is that before announcing it, we did already enter into commercial agreements to access QPUs. So we've got the supply, and we've entered into commercial agreements with one of the really cool and most innovative quantum developer ecosystems to provide the demand. And so when we launch Open Quantum on day one, we will have one of the biggest quantum communities feeding circuits into this open market right away. And so, yeah, we think the future is quantum. We think now that the future is decentralized. It took us, a little bit of experimentation to figure that out. And what we're maybe most excited about is that we think that the future is Bittensor. So, mic drop. I guess I'm done.
Wow, I think the crowd is very excited for that update. So I want to just hone in a little bit on the technology, and how are you going to, Crux wants this question more than me, probably. How are you verifying the organics? Like, you're using real quantum computers to do like spot checks on the occasional quantum organic problem. Is that right?
Yeah. So when we get into the organic phase, there's sort of two things that I want to call out. So the first is that when you're developing a quantum algorithm, you're using simulators and you're using quantum computers. And with the simulators, you're very often wanting like the perfect answer. Like, you want it to be executed in the way that mathematically it should be executed. Like, if you drew it on a whiteboard, you would come up with the right answer. And so when it comes to simulators, those are going to be validated using this proof of compute technology that we're inventing on 63, as 63 is operating with all of these synthetic circuits. And that works by, so the current version of that works by injecting a very small fingerprint into the quantum circuit that's essentially undetectable, manifests itself in the results. We then pull that fingerprint out, verify the fingerprint, and then take those results out of the results and hand them back to the user. So the idea being that if somebody were to, say, hey, I executed it, but they return you random results, you would know that they were lying to you. On the flip side, we don't know what the final answer is. We only know what the fingerprint is supposed to be. And so that's sort of that approach. Now, on the physical... Wait. Yeah, please.
So one of the greatest things about having you here on Bittensor is because when I was in university, my perspective, I did mathematics. My thinking was always that physicists were the smartest at uni, and you guys live up to that. So you're bringing unique ideas to our ecosystem. So tell me about this fingerprint idea, because this is valuable to other verification systems on Bittensor. So you funnel an organic to a computer, black box computer, and you've put some sort of, you've called it a fingerprint inside of the problem, and then you're able to withdraw that fingerprint and then give them the answer. Say more.
Yeah. Okay. So, and part of the fun of this is that, there's sort of like different ways to do security. Like you could just try to do security by obscurity and insert something that you think is kind of hard to detect. But one of the really great things about Bittensor is that like you have to open source it, right? Like validators are going to be running it. So it's got to actually be like a very good fingerprinting. But the current manifestation of this essentially assumes that we increase the computational load that's required by a couple of qubits. We use those couple of qubits to encode our own information in, but we understand exactly the impact that that's going to have on the output. So then you can detect that that fingerprint actually occurred because the execution actually happened, regardless of the final output. And I will say this is our current hypothesis about how this works, because the reason we're not moving forward with it immediately is because this market, as smart as this market is at innovating in the way you want them to, they're equally smart at innovating in ways you don't want them to.
Yes.
So we're trying to make sure that we have that really bomb. Now, Will, you can feel free to share a little bit more if you feel appropriate. Otherwise, I'd also be very happy to, abstain if you feel like it'd be better to hold it for the future.
Sure. Well, I mean, I will say, I mean, you've got like 90% of it, and but I will say just one little bit is that this sort of fingerprinting idea, we love building on work that's already been done. And this fingerprinting idea is sort of just I don't want to say just, it's kind of a recasting of the whole concept of quantum error correction and quantum error detection, because that's kind of the preeminent goal of what both of those schemes do. They want to say, is there a way that I can figure out what's happening in the circuit in a way that doesn't sort of harm whatever else is also going on in the circuit while it's running. And so the challenge is the challenge with all of these kind of error correction and error mitigation schemes is that you don't want to increase the computational load too much, and that's part of the theory that we're working on right now.
Yes, absolutely. That seems like the kernel of the difficulty of the problem. Like, yeah, how do you change the original problem, but you still get the output correct, and yet there's a fingerprint at the end? It sounds like something that can be solved in quantum mechanics, but not in classical computing. Because to me, from my classical computer brain, that just sounds impossible. But I actually will leave it to you guys entirely, and I don't think we need to dive too much farther there. Stefan, is the answer for organics and synthetics up to your standard?
I think I'll need to see the white paper on it, boys, to be completely honest. It's a really compelling line of thought, but I'd have to sit there from Thursday until Monday to really think about that answer. It seems that you guys have, you seem to have a line of sight and something kind of sacred to Bittensor, and I'd have to really sit on it to think about it a little bit more there.
Yeah,
I actually had another. Oh, sorry. Go ahead, please.
Well, I was going to say, so in addition to fingerprinting, as we move towards releasing that capability, we also have the intention of continuing to insert synthetics into the queue. So the key idea being, we want to validate every single circuit so that we don't have a terrible user experience where somebody, just goes and simulates every other and then returns garbage for some of them. But we're also sort of going to have a heartbeat that inserts data where we do know the answer to make sure that the entire thing is correct also. So, sort of having like a multi-layer QC process.
This is a unique encoding opportunity for quantum that's not really available in other domains. Would you say that's true?
I would say that that's the best initial hypothesis, yeah. That you very much are using, like Will said, essentially quantum error correction, here, which really may not be applicable. Though you may be able to zoom out and sort of ask if there's some analogy that could potentially be used.
I find it as both a relief and very encouraging that it took quantum computers to come up with the solution to organics, because it's really tricky.
Totally. Now, one of the things that I said, though, was that for simulators, the end user wants the right answer. And so we want to make sure that it's been faithfully executed using all of the laws of quantum mechanics. For real quantum computers, the current state of the market is that people don't actually, well, I mean, we would kill to get the right answer, but that's not what we're expecting from real quantum computers. Like we said in the early slides, they have very high error rates. It's very hard to get them right. And so what people are doing when they're submitting a job to a quantum computer is they actually want the exact wrong answer that the quantum computer is giving them. So you essentially, if you're trying to build out an algorithm, you do want to know how, in principle, it could work when quantum computers are good enough, but then you also want to know, like, how does it actually work for quantum computers today? And then you want to start applying error mitigation and error correction and see how the quantum computer does as you add those layers, so you can sort of say, how much can I juice out of this thing in its current state? And so while the simulators will have the fingerprinting, the QPUs actually will just get the job exactly as it's submitted, and before handing the response back out, we will have a closed loop verification with the platform. If that makes sense.
Yes, it does. It's very interesting inverse there, that you got the correct wrong answer. The exact. So the progress so far, so you've pushed up the number of qubits to, what was it, 26, 27?
27, I believe.
27. And this is by solving these peak circuits. And when it comes to, simulating that particular type of circuit, you said that it's like a really interesting one. There's a lot of entanglement. And so, you know that, like, the optimizations that are being done by the miners on the subnet are in fact like useful general solutions or general optimizations to simulations in quantum. That's part of the idea here, correct?
That's absolutely right. Yeah. Now there is so you can take sort of the in fact, let me just say that's a great way of thinking of it. So essentially, the hardness that we're encoding into the peaked circuits, it is so complex that essentially, unless there's something that hasn't been discovered yet, there's really not a way to do those and cheat. Like you can't be that smart because they are entangled so widely. I mean, never say never, but like those should be very, very hard to scale. If you look at the other, Will said when he was presenting that these are not necessarily representative of real quantum circuits, because real quantum problems actually tend to be a lot more sparse and like have entanglement, but not that hard and not that complex of entanglement. And so if we take a look at like HSTAB, that's sort of on this other side of the spectrum, where it's like, hey, if you can be really smart about analyzing this circuit, then you can make changes up front that allow you to simulate the thing really easily. Now, real quantum circuits sort of exist in between, where if you've learned these things, and if our mining community continues to educate, and if intelligence is sort of incentivized and decentralized, and we've got new thinking coming in because they can compete and take over from old thinking, that's going to essentially allow people to start to inspect quantum circuits as they come in, decide how they should simulate it, decide if they should pre-process it, and then potentially do a far better job by just having thousands of really smart people from totally adjacent fields working on these problems, instead of, like you say, physicists are smart, but like physicists also have been taught very specifically exactly how they should be doing things, right? And, don't necessarily take the same scrappy mentality that, non-physicists take.
That's a really interesting point. So what you're saying is the peak circuits are kind of like, I don't know, the worst case scenario, right? They're like the fully connected graphs or fully interacting systems where there's just no terms that you can brush under the carpet and ignore. So you're saying by preparing the network to handle peak circuit scenarios, which is like maximally entangled, maximally difficult wave function interconnections, the miners are presumably better positioned to handle real requests, which are, empirically speaking, these are much less complex requests than sort of peak circuits. Would that be a fair summary?
That is a very good summary. Now, it also, like, I will maybe add a little bit of detail to your answer to that, because essentially for a circuit of different nature, like for a circuit that is not as complex as these peaked circuits that we're generating, you may want to choose a completely different way to simulate them. So what Will had talked about NPS simulators. He had talked about tensor network simulators. The way that people are simulating these peaked circuits today are using something called a state vector simulator. So a state vector simulator, it doesn't get to benefit from any of the awesome data structures that Will was talking about. And instead, it uses like exponentially increasing memory to represent all possible quantum states with like zero approximation, essentially. Like it just calculates exactly what every quantum state should be. And so it's like a really inefficient way to simulate, but it's necessary for like sufficiently complicated problems where you can't afford to lose any of the information. So I think that it does represent one side of the spectrum, but we need to have, and this is why, again, one of the like many reasons, like if anybody, by the way, if anybody walks away from this being like, oh, 63 is not valuable anymore, like, you're missing the point totally, because 63 is where all the innovation comes that feeds into 48 in the execution environment. But miners are going to have to learn, when should I use state vector, and when instead is the circuit actually less complicated, and when should it when should it be run using an MPS simulator? And if I'm using an MPS simulator, I'm going to have all these different configuration parameters about like how much accuracy I'm willing to lose to the compression. So figuring out how to calibrate that, right?
Yeah, and I'll add on. Sorry, Bob.
No, please, Will, go ahead.
Yeah, I'll add on to this, because this is a great illustration of sort of what we mean when we say that sort of classical computing is sort of butting up against the edge of sort of what's possible, right? The difference between state vector simulators and MPS simulators, and say like Tableau simulators for Clifford, stabilizer circuits. So this is a great example of where algorithmic improvements are really what are needed for like specific kinds of problems. So like someone who's really clever and wants to do the best in every single situation will basically have to be able to both run a good simulation, but also analyze the circuit that they're supposed to run in the first place, and try to pick and choose whichever different strategy is best. And there's a huge diversity in terms of sort of what the data structures are like, and sort of their trade-offs. And what we're really trying to do is build a community that can really figure this out.
This sounds kind of familiar. What it sounds like is what you're saying is the miners are coming up with what I would refer to as expert systems, like heuristics that are dependent on certain circumstances where they can utilize efficiencies and advantages, which sounds a little bit like the early chess engines before AI was AI, where it was really just human encoded results that were just sort of, hard written into the code base. Do you see an opportunity for the miners to use actual AI? I guess I'll leave that intentionally open-ended. I'm not sure what form or shape it would take. But do you see miners being able to use AI to actually learn the right solutions to the sort of optimization problems that are presented within your challenges?
So, yeah, I think that's a very real possibility. There's a lot of there are so many degrees of freedom that I think personally, I actually think that AI is this might actually be like a perfect application of AI, right? To be able to do something efficiently. And analyze a circuit efficiently without having to do much work in terms of actually like starting a simulation on the circuit and figuring out that, oh, this is actually the bad strategy.
And
right.
Crux, I think you're sort of we should actually like hire you as our chief strategy officer, because you're basically laying it out, right? So imagine a world where, fast forward, we've made quantum computing resources free to the entire world of users. And because it is free for the entire world of users, because of Bittensor, all circuit submissions start to come through this thing. And we've got miners all around the world doing this stuff for scientists that's very hard, that they very often don't have the compute resources to do. And then on top of that, we're leaving a data trail, and that data trail is essentially every single circuit, a fingerprint of that circuit, which type of simulation performed, how that simulation performed, how accurate it was, how fast it was, what type of compute needed to be behind it. If you think about that data set, if you were to try to train sort of an intelligent simulation engine built to handle everything, that would be what you would need.
Sounds about right. So I believe Jake has silently left us. I believe there's other things to do. But I can back up and just ask one big picture question, and then I'm going to take a couple of questions from the audience. By the way, Bob, I wouldn't worry about people criticizing your work as useless and limited. I think you've left a pretty big blast radius in the chat here. People are salivating. People are very happy. I think it's a really, really interesting and deep story, and something that enriches Bittensor. So congrats, guys. It's been a really good talk. But a question from me is, I guess, so of course, most of the audience recognize that sort of CPUs are, very universal, very powerful, but not as optimized as dedicated hardware like GPUs. So where do QPUs, quantum processing units, fit into that sort of big picture here? Like, how big is the set of problems? How big is the market that quantum processors can really unlock for real use cases here? I believe there's, some people would look at this and say, well, quantum computers solve quantum problems, which is like molecular dynamics problems, or molecular science at least. But can you guys speak a little bit more about what the sort of addressable reach is of quantum systems?
Yeah, that's a great point. And so when we started off this presentation, I sort of gave that, the story of a conversation just a couple of weeks ago with one of these quantum computer companies. And again, there was this idea of, you want a quantum computer today, I'll sell it to you for a couple tens of millions of dollars. You want a quantum computer when I have 100 logical qubits, I'm not going to give it to you. So that's sort of because that 100 logical qubit level is the level that starts to unlock, the first about $10 billion problems. And so they don't do that today. We're not solving billion-dollar problems with quantum computers today. The problems that we are solving with quantum computers today are largely experiments. But there are hundreds of thousands of people out there trying to get access to these things. There are also a lot of companies, who have sort of seen the giant size of the prize and are making investments in quantum computing. And a lot of times, again, what they're doing is they have these two paths. One path is to say, let's start building out our IP portfolio around developing algorithms that solve our use cases, and we prove those out with simulators. And then at the same time, let's understand the resources that are going to be required. How good does a quantum computer have to be? And then let's test how good we can push a quantum computer to be today. The quantum computers that are out there, make no mistake about it, they're not solving real industrial use cases today. But the potential is so high and the trajectory is so hot that they are still one of the most expensive and scarcest resources on the planet.
Aside from cracking Shor's algorithm, can you give a concrete example of something that sort of, what is your Turing test for quantum computing living up to the hype?
Yeah, so I would say that a lot of the first value is going to be in simulating many body systems. So essentially, like, we think, we tend to think that we understand quite a bit, but actually there's a ton of stuff that we don't understand. Okay, so I'll say this, and then Crux, you can totally just shoot me down, or Will, you can shoot me down too if you if you guys can dispute this. But I was at Calgary on a panel yesterday at the IEEE Smart City World Conference just a couple of days ago, and this physicist tells me something, and I start Googling it because I don't believe her. She says, we don't actually understand how magnets work. And I was like, bullshit. Like, we definitely understand how magnets work. Like, we've got we use them for everything. We totally know how they work. She's like, no, we don't know how they work. And so I'm like, well, like, how have we gotten to where we are? And she says, well, like, we've basically gone and we've looked at every type of material that exists, and we've sort of tested them and we've understood them and what has what characteristics. But like, if you told me right now that I could synthesize a brand new material and, you know, I needed to synthesize a magnetic material that I didn't already know existed, I couldn't, because I don't understand how that stuff works. And so the first set of problems that quantum computers are going to be solvable is going to be to encode many-body systems into these computers so that you can understand essentially how nature works, like for these very small but very important problems, right? Now, Will, I would love your perspective on that, especially if it's different than mine.
Sure. Well, I would guess that there's a bit of hidden complexity in what the person you talked to said about not understanding how magnets work. We have pretty good theories, and they are very good in probably, I would say, like 98% of cases, right? But there is some hidden stuff that's still left to uncover in terms of material science research, right? And the question is obviously one of scale, but also of kind of exploring the space of like permutations of different materials and kind of the structure that goes into these interesting crystals, or I guess materials in general. This brings to mind the fact that on one hand there's the periodic table of elements. Every item on the table has its own kind of properties, but the space is obviously combinatoric when you try to put different materials together, and then it's made even more complicated by the fact that you can have different sort of physical structures at the microscopic level that each kind of add in their own properties. So what I would say, I guess, in terms of, I don't know, magnets, right, is that there's like a lot that we do understand already, and there's much more to explore still. As far as quantum computers go, right, this is a major use case that people are really looking into. Obviously, quantum computers are still subject to the scaling problem, and it's there's a lot of theory that has been already done, but we really need, this is sort of like a comparable to the interplay between theory and numerics, right? We can use a quantum computer to add in to essentially do like a big numerical simulation, but then the theory will eventually have to catch up and try to understand things from a scientific point of view.
Yeah, and I would also sort of point to this. So this is, again, DARPA's sort of circulating research from, I think it was Los Alamos National Lab, put out the original paper that studied all of these use cases in detail. But you can see in the colored version of it that there are sort of these colored clusters of problems. And so in the early days, if you sort of think about this balance of like quantum computer size and operations, this line kind of represents sort of like the first level of problems that are going to be unlocked. And so again, you can see that those are all sort of in the NMR simulation type range. You start to get into some kind of like Fermi-Hubbard dynamics and phases of magnetic materials and stuff like that. But for the most part, you're not getting into the super juicy stuff until a little bit later, right? Like, I mean, corrosive material, resistant material discovery, rocket fuel, right? These are very like, and then again, the red triangle that DARPA is tracking, RSA 2048.
I think in some ways, guys, you've made the work of opening the door to quantum research doubly hard, because the thing that plagues you guys is decoherence. Quantum matter just doesn't want to stay organized for very long. And you've chosen a decentralized system to try and cohere the decoherence. So you've kind of got like a lack of coherence at multiple levels in the system, and it seems like you guys have a plan. It's super interesting. But the last question I'm going to ask you guys about use cases, I think that definitely silenced the audience, is every miner in Bittensor right now wants to know how they can use your subnet to mine better. So let's talk about one thing that you mentioned very briefly earlier, which was actually trading and sort of market predictions. Can you just add a little bit more light to like how do you frame that as a quantum computing problem? Where's the advantage with that? How does that surpass AI in its current form?
Yeah. So some of the use cases would be things like, and by the way, most of those, I'm a little bit surprised. It seems like DARPA wasn't that interested in those problems, but I think the original Los Alamos paper did go into some financial use cases too. But those tend to be things like derivative pricing, right? Like basically looking at just a massive number of vastly interconnected dependencies and finding the optimal price, right? So those problems, like those types of optimization problems, are exponentially hard. They're extremely valuable. The quicker you can get to kind of like the ideal price, the more you can, trade at the right price before, while others are sort of mispricing it. And today those calculations are like super time intensive. They're always late. Like, I mean, weeks late sometimes, like behind schedule. And quantum computers, hypothetically at a big enough scale, would be able to do those types of things very quickly. You can look at really similar types of problems in like the insurance industry and the portfolio optimization industry. Like they all just sort of map very cleanly into some of the quantum algorithms that are out there. Now, I will also say that as you start to explore this space, you'll definitely find that not all quantum problems are created equal. So there are, I would say there are probably somewhere around like 10 really well-known types of problems that quantum is going to solve. And you can map lots of industry problems into those types of problems. But there are very few of them where the entire, world of quantum agrees that there's actually exponential compute advantage by doing them with a quantum computer. Shor's is one of them. So breaking RSA 2048, there's no, like nobody doubts that one is going to be possible at a sufficient scale. Number two is sort of some of the chemical simulations, many body simulations. The world believes that there's, huge advantage to that. When it comes to some of these bigger optimization problems, there are sort of the quantum bulls who think that there's going to be huge speed up with those. And there are also the skeptics who think that, you're going to have best case polynomial speed ups, or worst case, it'll actually be slower to run them on a quantum computer. And so, yeah, you guys still are on the bleeding edge of this. Like, in fact, if you think about like classical computers where we're all very comfortable today, in like the 1950s, a classical computer would take an entire room. It would cost the equivalent of millions of dollars. It would require like a team of scientists and engineers to run the thing. You really couldn't write software for them. I mean, you'd kind of try, but you'd mostly be like working with punch cards and stuff. And they were highly unreliable and they could only do very specialized tasks. That's kind of where we are with quantum computers. Maybe we're even a little bit ahead of that, where, yeah, they take up rooms, check. Teams of scientists, check. Millions of dollars, check. Kind of hard to program, check. But if you fast forward, right, from the 1950s until now, right, I have more compute power in my pocket than it used to take an entire room. And if we can start to set a sort of, similar trajectory with quantum computers, sincerely, our grandkids will live in the world that, we talked about at the beginning of this presentation, which is nuts.
Awesome. That gets me tingly. That's great. So I guess a final request from me, guys, is please incentivize your miners to share these wonderful innovations that they're making, either through bounties or through forcing them to load it, because this is clearly the secret sauce that's really important for the industry of quantum computing as well as Bittensor. So I'm going to leave that with you guys, and I'm going to cherry pick a couple questions that I've sequestered from the audience here. And then I think we're going to wrap because it's nearly midnight my time. So first question is from Mew called in Subnet 29. So did you guys calculate? I guess this is a benchmarking question about, it's all well and good to say miners are doing a great job on the 37 qubit synthetic problem in your subnet, but this only really matters and it's only worthy of hype and respect if you guys have carefully benchmarked what's the baseline here. Everyone that works in AI and machine learning is expected to benchmark how good is your model versus what's available off the shelf right now. In your case, I guess it's down to you guys to define the metric here that's been proposed is What are the flops that are required to do this using just brute force, stupid, use machine, calculate results versus what your guys are able to produce?
I would say right now, what our miners are doing in that area is pushing the boundaries of brute force. I think that's 37 is doable, pushing the bounds of brute force. Now, you can actually go peaked circuits. I'll kind of point some people at some other maybe money-making opportunities. I think it's still open. There was a company called Blue Qubit who had a hackathon where they put out a bunch of peaked circuits and challenged the community to solve them. Now, unlike us, where we're generating lots of peaked circuits, and you can kind of continually win, and the emissions are fairly high, they had a small fixed cash prize and peaked circuits of varying sizes. Those have failed to get beyond this. They've been open since this winter. So, and I mean, like, we've had the likes of IBM employees themselves focused on those types of problems. So I think, I think our people are doing pretty well with it. I don't think that on peaked circuits they have gotten beyond tuning simulators to work really, really well on large clusters of HPC. I do think there's still more innovations to be had there.
So I guess to paraphrase, they've gone from complete brute force to sort of Homo sapien brute force, where they select a smaller region of the phase space that's worthy of being brute forced.
Yeah. So if I were to be like extrapolating from information that the miners have been talking about in the public Discord, they're trying to address peaked circuits by sort of like using multi-GPU, by reducing precision so that they can fit sort of like more into the same number of bytes while still getting the right answer, and just by using the best state-of-the-art GPU. Now, all of those things are awesome. Don't get me wrong. That's like tuning the simulation to work on the environment, which is a very different approach than the approach that they took on the HSTAB. So HSTAB, they innovated so much that, like I say, we have to decommission the circuit now. But we are, I'm not going to share till we verify, but 37 is the highest verified count. We have information trickling in from Valley logs that we may have people going a little bit beyond that, but we haven't yet confirmed how they're doing it.
Okay, so you're
more to
optimistic.
come on that.
Sure, your optimistic trajectory here is they sort of find a signal here to determine where to double down on their efforts, and they sort of steer away from a really naive search over the space to something that's much more targeted. You guys are seeing some initial encouraging results suggesting that they're searching less of the space and are able to deliver results more quickly, but that's still sort of evolving. Yeah,
that's right. And that is, by the way, essentially our theory on how they're doing larger than 37, if that turns out to be verified.
I think it's broadly true for most of research, guys. I think that science is basically brute forcing its way through nature, and eventually we find tricks and shortcuts. But for the most part, it's just running out of stupid, dumb mistakes to search.
Yeah.
So I'm going to just choose one more question from the audience, and then I think we should wrap. This is a question regarding people that seem to be pretty motivated to support you guys. You've put on a clinic, so congrats. People want to know, I guess, you've introduced Subnet 48, which is going to be your sort of quantum compute lab. People want to understand a little bit better whether sort of one is the marketplace, one is the inference engine. Could you just disentangle these two a little bit more, just so that everyone understands sort of what they can expect from each of them?
Yeah, that sounds great. In fact, I'll maybe go even to some slides to help as we kind of talk about that. So when we talked about these subnets, we sort of laid it out like this. Before we did this, we had this important thing. So right now we're incentivizing innovation. We don't want that ever to die. Like we need that innovation to happen, because otherwise, I mean, what's really unique about an open quantum platform, like why do people need something like Bittensor for it? You could just, like anybody could scale up a large subsidized, compute warehouse. What we need is the two doing a dance together. And so the idea with the current hypothesis is that 63 continually challenges people to invent new provocative ways to solve bigger problems more universally, and that technology, as it is being invented, makes its way then into, it essentially graduates into 48 and becomes a backend that the end users can choose to run on there. And so essentially you're building your models on 63, then graduating your model to 48, where it can just be run and call it like a Docker container, essentially, by these operators servicing requests. And so it creates a huge opportunity for us to both incentivize, again, doing smarter things, continuing to push the state of the art of technology and enable that kind of future we were talking about, and also to incentivize operating. As we sort of looked at it, there was really no way to do it other than having two subnets, right? Otherwise, you sort of had to choose which of those things you were incentivizing.
I think that's a pretty
I don't know if
complete answer, guys.
Yeah, and I do suspect that this is a brand new idea. I think people we've thought about this a thousand different ways. I think people will look at this and say, yeah, that probably makes a lot of sense. I know there's going to be a lot of questions about the details, and the truth is that if we've learned anything about Bittensor, it's that you have to be sort of enter into everything with a plan. And then get ready to get punched in the face, because you're going to learn that your plan is going to hit very motivated people working very hard. And so we do have a solid plan on how we're going to do this. We have a sound model for how it's all going to work. We also imagine that as we start going, we're going to quickly learn and iterate and calibrate this thing to really be a well-oiled machine.
Yeah, and look, that's fully understandable. And I think just as important as a plan is there's precedents that you can learn from as well. Like Bittensor has, I would argue, solved certain market PMF fit problems around how do you feed innovation networks into deployment and hosting networks. So I'm not going to linger on that point. I think that I think, to quote you at the beginning of the call, like, we're not here to all reinvent the wheel over and over again. Tau has funded R&D. Tau has funded the creation of various mechanisms to deliver value from R&D all the way to productionization. So I think it would be prudent to look around and see how other subnets are teaming up to take the raw innovation plays and pipe those into deployment and hosting plays. And yeah, I guess I'd leave it there, guys. You've got a bright journey ahead of you, and I'm gonna call this one a wrap, guys. Thank you for joining us on stage. That was you put on a clinic. It was a really great chat. It's been a while since I've gotten into the details with quantum, so that was super fun for me on a personal note. Any last words from you guys?
No, I just wanted to thank you. If I understand correctly, you've played a strong role in the Bittensor ecosystem for quite some time, and again, from the outside looking in, I didn't know what I was getting into, but I've been very impressed with what I found when I got here. And while I initially imagined I'd dip a toe in, test the water, and run for my life, I find myself diving in headfirst and swimming with you guys. So thanks for building this beautiful ecosystem, and we look forward to changing the world together.
Yeah, well, I'll extend that thanks to the entire community. It's an awesome bunch of misfits that we've got here, and we're trying to fight the good fight. So that's one for everyone. Thank you guys for tuning in, and Novelty Search is a wrap. Have a good night, everyone.
Thanks.